morning. My name is Zoltán Kuszczyk. I'm a senior engineer in the Linaro Digital Home Group. So thank you for coming for this presentation. And what I'm going to talk today is actually integrating a commercial DRM with OP-TEE, Chromium, and encrypted media extensions. So I understand it's a very controversial topic in an open source conference to talk about DRM. So I took a red shirt, so if someone throws a tomato, it's not visible. But I will try to talk and convince people who, may think that DRM and open source cannot work together, that this is not the case, that actually doing open source and DRM together makes lots of sense. So, well, in Linaro we have a security team. The security team is working and investing lots of time on building a secure OS called OP-TEE. You will hear lots of sessions talking about that. Basically, it's using a technology on ARM that's around for more than 10 years, the ARM TrustZone, to basically write, deploy secure applications as secure OS. So the OP-TEE project is actually accessible through GitHub. You can go download the code, build it for emulator, for actual hardware, and start to develop your own secure applications. It's all open source. So we have OP-TEE, and also in Linaro we had it for a while. So we actually looked how OP-TEE can be vertically integrated into a DRM media playback solution. And we looked into the encrypted media extension standards, some of the requirements that we had from our partners, like dash support, dynamic adaptive streaming, and well, we actually integrated the encrypted media extensions using a project OpenCDM with PlayReady and TrustZone OP-TEE. So I put a small diagram on OP-TEE, but I need to emphasize there are better sessions to get internal information about it, or luckily Joachim is here, so he can correct me if I made a wrong statement anywhere. But basically, OP-TEE allows you to write a trusted application for the TrustZone, and your and a native application that's running outside of the secure OS. There is a Linux driver that allows the communication between the non-secure and secure OS. And luckily, there is already an API, the Global Platform API, that actually allows us to standardize this communication between the secure and non-secure OS. And there are various extensions, integration points already inside of the OP-TEE OS that allows to extend the OS itself. Well, working with, so I'm actually a client of the OP-TEE OS in a sense that I don't have much understanding of the internals, but if you go to GitHub, you check out the project, basically in a day or two, you can start to write a secure application. So you using C, you compile it, and with some magic, it actually loads into the TrustZone, and your client application can communicate to it. The nice thing about it that TrustZone is actually a hardware separation. So the ARM processor itself can do a context switch, when it switches between secure and non-secure mode, you have a nicely allocated secure memory area where only the secure applications can communicate with. So OP-TEE currently supported on many architectures, and on many boards and emulators, like on the ST, Allwinner, HiKey, MediaTek, and Texas Instruments. TI boards, some of the TI boards. So if you get one of these boards, you can start to play with OP-TEE. So now let's move forward with the encrypted media extensions. May I ask you to raise your hands if you already joined the keynote on the secure media playback? Okay, so you already got an introduction about the encrypted media extensions. Basically, the main goal of the EME is to allow playback secure video content directly from the browser using HTML5. So what it defines, and I need to emphasize, it's still a draft of the W3C, is that the HTML media element is extended with some additional elements that allows you to set up a secure playback. So shortly summarizing this quite complex diagram is that, you know, in an EME playback, obviously you have involved a web server, a license server, the provider of the content and the licenses. You have an HTML5 application that can be, you know, your own app, or you can use, for example, the Dash Forums, Dash.js HTML5 media player. You have a media stack that's part of the actual browser, and below that the content decryption module, which is actually specific to the DRM system, to the key system used by the actual content, and, you know, some platform-specific hooks below that. So if I want to summarize what this diagram does, is basically you obtain an encrypted media content, you set up a media session inside of the CDM. The CDM itself generates a license request. This license request sends so the license request is sent by the browser to the license server, and as a response, you get a response that used by the CDM to set up the actual DRM, CDM session for your media playback. After this setup is done, you're ready to decrypt your content. So that's happening inside of that loop. All right, now there is a problem with the EME spec, and there is an open bug on it. So actually, the W3C EME talks about how the web application should look like. What is the API that the web application should use? And it doesn't specify how the browser implements it. So there are some requirements for the security of the CDM and so on, but it doesn't define how a CDM should look like. What should be the API or the interface towards to the CDM. And that's a little bit of problem because there are various DRM systems which have various requirements to set up a session. And the EME spec itself doesn't really observe and makes differences between the various DRM systems, which actually causes a problem to make sure that the EME specs allows interoperability between these DRM solutions. So one of the approach that actually Microsoft proposed and they implemented a reference implementation is actually defining a CDMI interface which tries to be generic to allow the integration of different DRMs. And also, it actually abstracts the CDM away from the browser. So it says that, okay, the CDM itself implements an IPC service, and the browser is just a client to it, which means that, you know, once you create an OpenCDMI service, you should be able to integrate the same service with different browsers. So at Linaro, we actually got involved in porting OpenCDM to ARM and integrate it with Chromium. So what we did next to the mock DRM implementation, that's just a dummy CDM implementation in OpenCDM, we created multiple CDM implementations for the Microsoft PlayReady, for example. And we also created 2 additional CDMs, a ClearKey OP-TEE CDM and a ClearKey OpenSSL CDM. Now, the point of why we needed multiple CDMs is that obviously the PlayReady code itself requires a PlayReady license. So the work done in that direction cannot be fully open source. And as such, it makes it very difficult for us to work with all of our partners to make sure that they benefit from the work that we do on CDM. So to solve this issue, we created a ClearKey OP-TEE integration. So basically, a ClearKey CDM that does the decryption using OP-TEE, and a ClearKey OpenSSL CDM that does the decryption using the standard OpenSSL libraries. So basically, the OpenSSL CDM allows us to test the interoperability and portability of the OpenCDM between different CPU architectures. So this one runs on x86 as well. And the ClearKey OP-TEE CDM allows us to exercise and test the full EME path OP-TEE-based decryption without the involvement of a commercial DRM solution. And the PlayReady is actually our demo and or proof that OP-TEE is actually can be used nicely with a commercial DRM. So I have a table here that kind of summarizes the different modules that we created. So the first one, the Chromium external ClearKey, this is a CDM that's part of the Chromium project. So you can actually test it out on any Chromium or Chrome build. I will try to demonstrate that. So for example, if you go to this webpage -if.org, you will see you can find the demo of the Dash HTML5 player. You can select various media streams, like let's say the CableLab ClearKey. So all Chromium and Chrome builds have a ClearKey CDM integrated. And if you click on play, actually you can see that the page reports that we are using the key system ClearKey. This is the current key ID and the actual video type. So in a case that you have a PlayReady or Widevine CDM enabled in the browser, you can play back the remaining streams as well. So this is basically the first CDM implementation. And as you can see, the next ones, the ClearKey CDM basically is utilizing the OpenCDM, but it doesn't utilize the OP-TEE PlayReady, and it can be built and used on ARMv6, ARMv7, ARMv8, and x86. We have the next CDM with the OP-TEE one, which utilizes the TrustZone, but no DRM and PlayReady support, and the Linaro CDM, which has, oh, what's happened? The Linaro CDM, which has support for PlayReady. So now you may ask that at Linaro, are we doing PlayReady? Are we doing Microsoft code? Are we contributing back to Microsoft, or we modifying heavily the Microsoft PlayReady code? And my answer is no. Actually, the Microsoft PlayReady already comes with a CDMI interface that's fully compatible with the OpenCDM. So all what we need to do is basically build the Microsoft PlayReady to the ARM platforms. Obviously, make sure that there is an integration level with integration with OP-TEE. But outside of that, the integration point with the OpenCDM is through the CDMI.h interface. So, good part of our work on the CDM and OpenCDM is now upstream to the main project maintained by Front of Focus. The OP-TEE-based CDM we have running on various platforms. So actually with the 96 boards we still experience some graphics issues which are related to Chromium, but we are currently solving it. And this is just a very basic diagram showing how the PlayReady porting kit tree is integrated with OP-TEE. So luckily the Microsoft PlayReady, the PK3, the latest one, has already support for TEE-based video decryption. So it was fairly straightforward to get the integration done with OP-TEE. So also you may be wondering that why Microsoft came with TEE support just recently. And actually there is an interesting thing about the emerging of the 4K video content. So before the 4K video content, you could get around to have a software-based DRM to playback HD content. With the 4K video content, actually the studios came with a much more strict requirement that the decryption actually needs to be done in hardware. And as such, DRMs today need to move in a direction where they have a proper support for trusted execution environments. So in our demo that you can see later, basically we show that we are capable to play back any PlayReady protected streams using Chromium. You can actually build Chromium fully from open source, build the OpenCDM from open source, and just communicate through an RPC to the PlayReady enabled CDMI service. But actually what remains an open question and an open problem is that currently in our PlayReady CDM solution, we are cheating a little bit. So the DRMs themselves require that once you decrypted the content inside of TEE, the content stays inside of the TEE. So that means that your video data path is fully secure from the point where you decrypted the content up to the point the renderer displays on the screen. So right now in our demo, we are cheating a little bit, as I said, that we're just returning the clear buffers back to the user space to demonstrate actually that the EME integration is in place. So what remains to solve is actually to kind of standardize the way how the secure media playback is implemented on Linux and ARM. And we have several concepts for this and also prototypes. where we see some challenge how to make those changes, how to implement a secure media playback in a way that it can go upstream to the Linux kernel. So other CPU architectures can also benefit from the proposed architecture. But what we see currently, the best possible way to solve it is basically integrating the existing DMA buffer sharing mechanism in Linux with secure extensions, so that the CDM itself returns an obfuscated pointer, or precisely say the DMA buff file descriptor that points to the secure memory region, which is passed forward to the player, and the player, you know, like let's say a GStreamer handles the actual buffer and passes down the DMA buff reference to the actual DSP, which is linked which is allowed to access the secure RAM and basically do the actual decoding and displaying on the screen. So that's a remaining task that we are currently solving. So I think that's all from me, and I'm looking forward for your questions.
So that you've integrated PlayReady 3.0. In your demo, you mentioned that you integrated PlayReady 3.0. The DRM that's implemented on top of OP-TEE, does that implement the entirety of PlayReady 3.0, or have you followed Microsoft's recommendation for porting only the T part, whatever's underneath the T layer?
Yes, so basically in the demo we are using the default Microsoft implementations of the various T functions. So when we talk about like integrating key storage or AES decryption, we are using currently the default implementations that are coming with PlayReady. Obviously, it has the feature for replacing this in a quite straightforward way, and that's something we are looking into. Science on one of the boards on the B2120, we also have hardware decryption support, so we want to enable that. But currently we are analyzing which parts we need to replace, which parts we can keep. Also, there were various advancements on the secure key storage done by Joachim's team. So we still need to coordinate on that how that comes together with the PlayReady integration.
I'm Petr Peterka from Verimatrix. The open CDM, does it have interfaces to the video pipeline in the on the chip? And you also mentioned the decryption, or do I have to do most of it in software?
So the OpenCDM itself is pretty much matching the type of interface that you see on the top of the EME spec. So you have you basically setting up the media sessions, passing down the keys, and it doesn't really specifies any fine-tuned decryption features. So the decryption itself is passing down a buffer, some descriptors around the buffer, and the decrypt function returns a clear buffer, which may be anything, depending on your DRM solution. So in all cases, that's going to be a DMA buff reference, but it can be a different type of content that describes your decrypted buffer.
But I think your question was more towards the OpenCDM interface with a media player as well. And
That's part of it, yes.
right, so, and I believe in the OpenCDM specification, when you look at the open source project, it does include the media player as well in terms of that layer. When you look at the, the OpenCDM specification, you see that there's the media player and then the handling of the decryption buffers as well, I believe.
Yeah, so.
Well, basically, the only interface inside of the OpenCDM is, yeah, I know what you mean now. So the OpenCDM has a browser part of implementation, and it has the CDMI implementation connected with an IPC. The browser part itself, the one that actually integrates the media player itself. So in our demo, that's the standard internal Chromium media player. But you can choose to use a different type of player. That depends on the browser CDM implementation that you choose. The CDMI service itself doesn't know anything about the player. So it returns buffers, and it has also callbacks where you say that, okay, the secure processor needs to free up the buffers now.
So the parsing happens outside of CDM. If I have a stream that has audio and video, and somebody needs to figure out is audio in the clear or encrypted, or is video encrypted, that's all happening outside of
Exactly.
Okay, understood. Thank you.
Exactly.
Can you talk a little bit more about how you plan to maintain the confidentiality of the stream once you leave the encrypted data, I guess, protected? So you talked about you pass it back in the clear now, and you talked about a strategy to move forward where you wouldn't pass that back because of the requirements that have been placed by studios. Can you elaborate on that just a little bit more? So you said that once the data is decrypted, the studios or whatever your requirements are, it says it's supposed to maintain or be maintained inside of TrustZone, and you described a path forward for meeting that requirement. Can you elaborate on that a little bit? I wasn't quite sure on how you talked about obfuscating the path back and then allowing the player to read from some secure RAM that's available to it. Can you just talk about that a little bit more?
Yes, so the point of integrating a secure media playback and utilizing, for example, a DMA buff to attach or reference a secure buffer from the non-secure space. The main motivation of that is actually to get most of the video playback, secure media playback related software into the open source space. So that means that you have certain DRM solutions which an OEM buys, and it's a black box. You just throw something to the secure processor and something displays on the screen, and nobody knows what's going on. So the point of us providing a secure media path is to allow you to have your own media player, to implement even use cases where, let's say, you have a decrypted buffer which has a header, and with some IP blocks you can even protect the buffer data, but keep the header in the non-secure space, which means that your media pipeline still can be inside of the non-secure space, parse the headers, pass towards the the decrypted buffers in the media pipeline and basically pass down the DMA buff to the DSP whenever you need to process the actual buffer. So that's the main goal here.
Maybe you can say something about with TrustZone, how you carve out these memory regions with these memory protection, address space controllers, and then you just point these, you have those file descriptors that the player sees, but all of the decrypt, decode, rendering is, all those buffers are in secure space. And then an HDCP on HDMI out to the monitor. So it's really this obfuscation or this file descriptor that gets passed back to the player, and it kind of marches everything through the pipeline, but all the operations should be happening in memory space that has been designated as secure and cannot be accessed through user space. So it's this file descriptor that you go, okay, decrypt, this is very simplistic, decrypt, decode, render. So you see that file descriptor in user space, but every step of that operation is taking place in memory that has been designated as secure that can't be accessed by the user space. So that keeps the buffers.
The actual device. The device accessible, whatever's doing the actual rendering, is the device accessible inside of the secure world or inside of TrustZone?
It's how you architect the playback and the components of that playback. So the actual media pipeline is part of your solution, but you have to architect it properly such that all those decrypt, decode buffers never are accessible to user space. So the example that he's giving with like DMA buff, so that's what we're looking at, keystream or DMA buff, is our implementation, but we have to implement it such that it's all those buffers are carved out of secure memory.
So you've only talked about the two ends of the problem in that you're putting it, you're decoding it into secure memory, and then at the end you're taking it from secure memory and outputting it over HDMI or whatever. But in the normal case for graphics, there's a hell of a lot of agents in between. I mean, you've got your windowing system or an Android Surface Fling or whatever that's wanting to do compositing that needs to understand this. Have you looked into all of those agents and what needs to be changed in there?
So in the case of Android, you already have a concept of a secure buffer and secure surface, which is passed from the media player to the hardware composer itself. So you can solve it on the compositor level how you should handle that particle buffer. So if you need, do things like positioning and rotation or whatever, you can have your custom implementation in the hardware composer to achieve that. So that's in case of Android. In our demos, we are using Wayland with a DMA buff extension. In case of Wayland, there are no standard ways for basically marking a surface as a secure. So that's something that we need to look into.